There is a silent hazard lurking underneath our major global cities, and our buildings were not designed to handle it. A new Northwestern University study has, for the first time, linked underground climate change to the shifting ground beneath urban areas. As the ground heats up, it also deforms. This phenomenon causes building foundations and the surrounding ground to move excessively due to expansions and contractions and even crack, which ultimately affects structures' long-term operational performance and durability. Researchers also report that past building damage may have been caused by such rising temperatures and expect these issues to continue for years to come. Although rising temperatures do pose a threat to our infrastructure, the researchers also view it as a potential opportunity. By capturing the waste heat emitted underground from subterranean transportation systems, parking garages, and basement facilities, urban planners could mitigate the effects of underground climate change as well as reuse the heat into an untapped thermal energy resource. The study will be published in Communications Engineering, a Nature Portfolio journal. It marks the first study to quantify ground deformations caused by subsurface heat islands and their effect on civil infrastructure. Underground climate change is a silent hazard. The ground is deforming as a result of temperature variations, and no existing civil structure or infrastructure is designed to withstand these variations. Although this phenomenon is not dangerous for people's safety necessarily, it will affect the normal day-to-day operations of foundation systems and the civil infrastructure at large. Chicago clay can contract when heated like many other fine-grained soils. As a result of temperature increases underground, many foundations downtown are undergoing unwanted settlement slowly but continuously. In many urban areas around the globe, heat continuously diffuses from buildings and underground transportation, causing the ground to warm at an alarming rate. Previous researchers have found that the shallow subsurface beneath cities warms by 0.1 to 2.5 degrees Celsius per decade. Known as underground climate change or subsurface heat islands, this phenomenon has been known to cause ecological issues such as contaminated groundwater and health issues including asthma and heat stroke. But until now, the effect of underground climate change on civil infrastructure has remained unstudied and little understood. The researcher says if you think about basements, parking garages, tunnels, and trains, all of these facilities continuously emit heat. In general, cities are warmer than rural areas because construction materials periodically trap heat derived from human activity and solar radiation and then release it into the atmosphere. That process has been studied for decades. Now, the researchers are looking at its subsurface counterpart, which is mostly driven by anthropogenic activity. In recent years, the research team installed a wireless network of more than 150 temperature sensors across the Chicago Loop, both above and below ground. This included placing sensors in the basements of buildings, subway tunnels, underground parking garages, and subsurface streets like Loria Drive. For comparison, the team also buried sensors in Grand Park, a green space located along Lake Michigan, away from buildings and underground transportation systems. Data from wireless sensing network indicated that underground temperatures beneath the loop are often 10 degrees warmer than temperatures beneath Grand Park. Air temperatures in underground structures can be up to 25 degrees higher compared to the undisturbed ground temperature. When the heat diffuses toward the ground, it puts significant stress on materials that expand and contract with changing temperatures. The researchers used Chicago as a living laboratory, but underground climate change is common to nearly all dense urban areas worldwide, and all urban areas suffering from underground climate change are prone to have problems with infrastructure. After collecting temperature data for 3 years, the researcher built a 3D computer model to simulate how ground temperatures evolved from 1951, the year Chicago completed its subway tunnels, to today. He found values consistent to those measured in the field and used the simulation to predict how temperatures will evolve until the year 2051. The researcher also modeled how ground deforms in response to increasing temperatures, whereas some materials, soft and stiff clay, contract when heated, other materials, hard clay, sand, and limestone, expand. According to the simulations, warmer temperatures can cause the ground to swell and expand upward by as much as 12 millimeters. They also can cause the ground to contract and sink downward beneath the weight of a building by as much as 8 millimeters. Although this seems subtle and is imperceptible to humans, the variation is more than many building components and foundation systems can handle without compromising their operational requirements. Based on computer simulations, the researchers have shown that ground deformations can be so severe that they lead to problems for the performance of civil infrastructure. It is not like a building will suddenly collapse. Things are sinking very slowly. The consequences for serviceability of structures and infrastructures can be very bad, but it takes a long time to see them. Because urban planners and architects designed most modern buildings before underground climate change emerged, they did not design structures to tolerate the temperature variations we experience today. Still, modern buildings will fare better than structures from earlier time periods such as the Middle Ages. Going forward, the researchers said future planning strategies should integrate geothermal technologies to harvest waste heat and deliver it to buildings for space heating. Planners also can install thermal insulation on new and existing buildings to minimize the amount of heat that enters the ground. The most effective and rational approach is to isolate underground structures in a way that the amount of wasted heat is minimal. If this cannot be done, then geothermal technologies offer the opportunity to efficiently absorb and reuse heat in buildings.